All right, so in this unit, which is called stoichiometry, we're going to learn about using a balanced chemical equation, kind of like a recipe, to determine how much reactant we need to produce a certain amount of product. And actually, in the end, that'll be one of the things that you're graded on is how close can you come to making a specified amount of a product from a reaction. So if we look at a recipe for chocolate chip cookies, for example, so if you really wanted some chocolate chip cookies and you had one egg, but the rest of the ingredients you had plenty of, and we have this recipe, we know it makes 5 dozen cookies, right? Well, if the recipe calls for 2 eggs, you only have one, of course, it's kind of intuitive. You know that if you're going to keep the recipe and all the ratios correct, you're going to make 2.5 dozen cookies instead of 5. You're only going to need 1/2 of all of these ingredients. So a half a teaspoon of vanilla extract, 1 cup of chocolate chips, and so forth, right? That's something that is pretty straightforward, but stoichiometry works the same way for chemical reactions. So, for example, if we look at a reaction like hydrogen, 2 hydrogen plus oxygen yields 2 waters, what does that mean? Well, we normally would think of it as 2 hydrogen molecules reacting with 2 oxygen molecules, right? And resulting in 2 water molecules. That's what the balanced equation means. And we can see visually that it's balanced because there's a total of 1, 2, 3, 4 hydrogens on the left, and there's 1, 2, 3, 4 hydrogens on the right, and the same with oxygen, 2 oxygens, 2 oxygens. So we think of a balanced equation as being like this recipe that calls for, a certain ratio of molecules or atoms. But because atoms and molecules are so tiny, unlike cups of flour and sugar, um, we have to put them together a little differently. In other words, we have to use something called the mole. So instead of trying to react 2 molecules of hydrogen with 1 molecule of oxygen, which would be impossible, they're way, way, way too tiny, we have to group them together into these things called moles. And a mole is just a counting unit. And if you've never heard of a counting unit before, the most common one that we probably use in day-to-day life are dozens. You don't buy eggs 1 egg at a time, usually you buy them by the dozen, right? The same thing with maybe, in some cases, donuts or roses or whatever. You group smaller, relatively cheap things together to into larger counting groups, right? And so that's what the dozen represents. It represents 12 of something. Well, a mole is a similar concept, but having 12 molecules just wouldn't be substantial enough. Even if our counting unit for molecules was like thousands or billions, that would still be too small of an amount for me to actually weigh in a reaction, or excuse me, to try to put together in a reaction and react. So instead, we have this huge number, 6.02 times 10 to the 23rd power. So a mole is just simply equal to that many of something. And technically, it could be anything. It could be, tennis balls or, cars or, drops of rain or whatever. But all of those things are way too big to actually have such a huge amount of. 6.02 times 10 to the 23rd is such a big number because it's only used for counting really, really, really small things and grouping together really, really, really small things like atoms and molecules. We call it Avogadro's number in honor of a chemist who, did some important things long, long ago, Amito Avogadro. But the number 6.02 times 10 to the 23rd is just a counting unit. So you don't have to write this down, but just how big is this number, 6.02 times 10 to the 23rd? As an analogy, if you had that many grains of sand, so like I think of a tiny little grain of sand, like a half a millimeter across, it would be enough sand to fill the Great Lakes twice over. Okay, so just imagine the volume of all of the Great Lakes together. and then double that, and that's how much sand you would have if you had 6.02 times 10 to the 23rd grains of sand. So is that a big number? Yes, that is a huge number, right? You could also say that that amount of sand would cover the entire United States to a depth of 13 feet. So it's a huge, huge amount of anything. But because um, we look at small particles like atoms and molecules when we talk about moles, a mole of water molecules only occupies about 18 milliliters. So it would barely be a drink of water. All right. And so what that illustrates is a water molecule is trillions and trillions and trillions of times smaller than even a grain of sand, which is already pretty small. And so that's why we need such a huge number for grouping together such tiny, tiny things. Okay, so why that weird number? Why 6.02 times 10 to the 23rd? Why didn't we use something else? And the answer basically is we already were using these masses from the periodic table, like 12.011 for carbon. We were saying that one carbon atom weighs 12.01 AMU. So we had a periodic table full of these atomic masses that describe the mass of the average atom of that element. And so instead of coming up with a new number to describe what a mole of something would weigh, we basically said, or chemists said long, long ago, why not just reuse the mass that's already on the periodic table? In other words, how many carbon atoms would be equal to 12.01 grams? We already know that one single atom weighs 12.01 AMU, and so that's why that number is on the periodic table in the first place. Why not just recycle that same number and use that again, okay? And instead say, all right, let's group together enough carbon atoms so that it weighs 12.01 grams, right? So that would then be a mole. So 6.02 times 10 to the 23rd carbon atoms would be 1 mole of carbon, and it would weigh 12 grams or 12.01 grams, right? Magnesium, if you have a periodic table handy, you'll see that its atomic mass is 24.31. And so 1 mole of magnesium atoms weighs 24.31 grams. Chlorine, same thing. 6.02 times 10 to the 23rd chlorine atoms equals a mole of chlorine, which equals 35.45 grams of chlorine. Again, we're just getting these numbers from the periodic table. We're just reusing the atomic mass that's already there to describe the mass of a mole of these substances. And then finally, water molecules. If I have that many water molecules, you can say that you have a mole of H2O, which weighs 18.02 grams. Now, water, of course, is not on the periodic table because it's a compound, right? So you actually, to get this 18.02 number, you actually have to look at oxygen, which has a mass of 15.999, or basically 16, right? And then you also have to look at hydrogen, and each hydrogen has a mass of 1.008, or 1.01 if you round to the nearest hundredth. So if you take the mass of an oxygen, or a mole of oxygen atoms, and then you look at also adding to that hydrogen, which is 1.01 grams per mole. But the problem is it's H2O, so of course we have to multiply the mass of hydrogen by 2, and that is where we get that 18.02 number from. It's just 16 plus 2 times 1.01, or 2.02. So that's where the number 18.02 came from. So the mass in grams of 1 mole of a substance, whether it's an element like carbon or a compound like water, is referred to as its molar mass. And that's an important thing to understand, because when we understand what the molar mass of something is, we can use a scale or a balance to actually count atoms by weighing them. So if you're doing this reaction and you actually wanted to use 2 moles of aluminum in this reaction to go along with 3 moles of copper 2 sulfate, well, what would that look like? How would you count that out? That's way too many atoms to count out. Well, if you know that 1 mole weighs, according to the periodic table, like 26.98 grams, well, 2 moles would weigh double that, which is about 53.96 grams. Okay, so that's how we use this concept of the mole to allow us to count atoms and molecules by weighing them. If we know the mass of a mole, we know how many of something are in a mole, then we can use the balance to know roughly how many of those atoms or molecules that we have. Okay, so last thing here, let's talk about doing conversions between mass in moles. So a molar conversion might be converting from grams of something to moles. So for example, we might be asked the question, how many moles of sodium would weigh 50.0 grams? All right, so we would set it up as a conversion. So if you remember from first semester learning how to convert between like meters and millimeters or grams and kilograms, we use a process called dimensional analysis where we multiply fractions to convert and cancel units that we want to get rid of. So if I have 50 grams of sodium as my starting number, I want to start by writing that. I'm going to multiply that by a fraction, okay? And then I always want to get rid of whatever I'm starting with. So if I have grams of sodium as my starting unit, I want to get rid of grams of sodium. So it's going to have to go on the bottom of the fraction that I'm multiplying by, right? And then since the question is asking me how many moles of Na, that means moles of Na would have to go on top. So that in a second here, when I go ahead and multiply across the top and divide by what's on bottom, grams of Na will cancel because it is both on top and bottom. Now, if I look at a periodic table, I can figure out the numerical relationship between grams and moles of sodium. So 22.99 would be the number of grams in 1 mole, right? So that becomes the number that goes next to grams, and then I put a 1 next to moles because that's what that number means. It means the number of grams per 1 mole. Now I can cancel grams of Na, and I'm left with moles, which is what the question is asking me for, which means it's time to write my equals sign and get out the calculator and do the calculation. And so I don't have to multiply 50 by 1 because that's just 50, but I do have to then divide by 22.99. So 50 divided by 22.99, and then I'll round it for 3 significant figures, just like my 50.0, gives me 2.17 moles of sodium. And you can do a mental check. 50 grams clearly is, over 2 times the mass of a mole of sodium, so it makes sense that we have a little bit over 2 moles. All right, let's try another example. This one we're going to go from grams all the way to atoms. And so how many atoms of gold would weigh 1.95 grams? Doesn't sound like it would be that many, but it's probably going to give us a pretty big answer because we're talking about atoms, which are extremely small. So in all of these conversions, we always start with the number we're given is going to be in our starting place. And then we're going to multiply that by a fraction. So think to yourself, all right, what unit is going to go on the bottom of my fraction bar here? What unit am I trying to cancel? And that, of course, is whatever unit I'm starting with, right? In this case, grams of AU. Now, I would like to go to atoms. So I'd like to put atoms AU on top. The problem with that is I don't know the mass of a single atom of gold in grams, right? So this is where I'm going to go to moles, and then from moles, I might be able to go to atoms. So if I put moles on top, just like up above, I do know the relationship between moles and grams. It comes from the periodic table. And if I look up gold on the periodic table, it has a mass of 196.97. And so that number goes next to grams, a 1 goes next to moles, and we can cancel grams. So this problem, though, has another step because if I look at the unit that's uncanceled, moles of AU, it is not the same as the unit I'm being asked for, which is atoms. So I need to get rid of moles, so I need another step. So moles of gold goes in the bottom, and then atoms of gold, which is what I'm looking for, will go on the top. And I do know the relationship between moles and atoms. It doesn't come from the periodic table, right? We already used the number from the periodic table. The relationship between atoms and moles is that there are 6.02 times 10 to the 23rd atoms of gold, or really anything, in 1 mole, right? That's Avogadro's number. And then I can cancel moles because it shows up on the top and the bottom. And I am at atoms of gold, so I can go ahead and write my equal sign because I'm done setting up the problem. It's time to get out the calculator. Now in the calculator, it doesn't really matter what order I go in. 195 can be multiplied by Avogadro's number and then divided by 196.97, or you can divide first and then multiply. It doesn't really matter, but you should get, and again, you'll need a scientific calculator for this, or you can use, one on Desmos or on your computer, but you should get a very large number, 5.96 times 10 to the 21st gold atoms, which makes sense because it's a huge number because we're talking about atoms, but it's still way less than a mole of gold. And if you look at our starting number, 1.95 grams is almost exactly 1/100th of a mole of gold. All right, one more we'll try here. What's the mass of 2.50 times 10 to the 23rd water molecules? So just like always, we're going to start with whatever we're given, but we're going to make sure we label it, right? H2O molecules. And so we definitely want to get rid of H2O molecules, so it has to go on the bottom so that when we divide, it cancels. Now I'm going from molecules this time. I want to go to grams because the question is asking me for mass. But I don't know the mass in grams of a single molecule of water. I do know the mass in grams of a mole of water molecules, or I can find it. So that's what I'm going to do. I'm going to go to moles first. So if we think about this relationship, I'm talking about Avogadro's number, 6.02 times 10 to the 23rd. That would be how many water molecules there are in 1 mole, right? So just like I did up here with atoms, anytime we're talking about how many of something are in a mole, that's where we're going to use Avogadro's number, 6.02 times 10 to the 23rd. So that's going to cancel water molecules. And if I were to stop here, my answer would be in moles. So I need to keep going because I'm trying to get to mass, right? I'm trying to get to grams. So I have one more step, and that is to go from moles to grams. And if we think about it, we actually already did this problem just previously. Up above on the page, you should be able to see that the mass of 1 mole of water molecules is 18.02 grams. So we got that from the periodic table, adding up 2 hydrogens and an oxygen. That then cancels moles of water. And since I'm at grams, which is what I'm being asked for, right? I'm being asked for the mass. I can go ahead and write my equal sign, and I can do my math. This time I have to divide by Avogadro's number and multiply by the molar mass. And so I come up with 7.48 grams of H2O. And that's just an introduction. We're going to do a lot more practice. So if you didn't quite catch on, you can watch this again, or also, again, we'll go through this, bring your questions to class, and we'll go through plenty more examples.